Okay. Yeah. Okay. All right. Thanks for that. Now we should be good. Okay. So we started talking about Boolean circuits. They were great, but they had a limitation that they couldn't handle inputs that were growing, right? If you had to build a multiplication circuit, okay, maybe I'll build a circuit for 25 inputs. But tomorrow, if someone comes and says, okay, I need to multiply this 10,000 bit numbers, then I have to redo the circuit in some sense at least. Okay. So our goal was to then build a model which can handle inputs that would grow, right? Unbounded length inputs. I mean, still finite length, but I don't know a priori what size inputs I'm going to work with. There's no upper bound. And towards this, we came up with, one of the simplest kinds of algorithms that we can think of, right? Which was single pass constant memory, meaning, I'm just passing, going through the input one bit at a time. And then each bit, I just store some constant amount of information. Okay. And so with this led to the definition of what we call deterministic finite automaton. So deterministic, because the transitions are somehow deterministic, right? I see a bit, I'm in some state, my next action is predetermined. There's no real choice there, okay? And finite, because the number of states is fixed a priori. It doesn't depend on the input length. Automaton, just because it sort of seems like it's something that a robot would do, okay? These are very, very old, but still not as old as Turing machines, which is coincidental. And the definition, recall, had two important ingredients. The most important one was the transition function, T, right? Which takes a state you are in and a bit that you're reading, and then tells you which state you're going to jump to next, okay? So once I know this transition diagram, I'm pretty much fixed, right? And once we had the definition, we also define what it means to have a function, right? A function computed by a DFA. Okay, so I have a function, then we say a DFA computes f if for all x, d of x equals f of x. Okay. So, I have now a function, a way to compute certain kinds of functions on all size inputs. So let's now try and investigate what's the power of this computation model. What can they actually compute and what they cannot compute, more important. And I also said that, as a matter of terminology, functions which output a single bit are really equivalent to languages. The terminology of languages comes from logic and linguistics, but in computer science, for me at least, functions seem more natural, right? I have some specification that I have to match. And language really is just a collection of strings. Okay. Any questions about this setup? Okay. And we saw one example of a DFA in last class, right? Or actually, we saw two. So example one was a DFA to check, actually, to compute the XOR function. Right? And example two was a DFA to check if number of ones was divisible by 3. Okay, maybe okay, all right, I'll scream at the loud top of my voice with a mask on. If you can't hear me, let me know. Okay, So we had these two examples, a DFA to compute XOR function and a DFA to compute whether the number of ones in the input string was divisible by 3. Okay? And it's actually a lot of fun to play with DFAs and to kind of come up with deterministic finite automaton which compute certain functions. Okay, so to get a sense of what we can and cannot do, let's do a few more examples, and then we'll start talking about more sort of fundamental questions about this new computational model that we are looking at. Okay. So here's a question for you. I'm going to define a function, and I want you to come up with a way to compute it by deterministic finite automaton, right? And the function is the following. It takes an arbitrary length string as input, okay? And it does something, somehow seems rather simple, but at least it's a good example to think about. It just checks if the string X ends with a 1 at the very end. Okay. The only thing it's supposed to do is, take your entire input and see if the last bit is a 1 or if the last bit is 0. That's it. If it's a 1, you have to say 1. If it's a 0, you have to say 0. All right. So how can I compute this using a deterministic finite automaton? Any suggestions? Yeah. Okay. All right. So let's start with, we always need to start somewhere. We always draw the start state first. And in this case, the start state for us always is 0. You could change it, but just for standardization, we're going to say the start state is always 0. And now, if you're trying to design an automata, always think like one. Don't just pretend to be one, but really become one, which is think what the automata is going to see. You're just processing some bits one at a time, and you need to keep only a constant number of bits in your mind. Okay, and based on that, you have to make your decision. So in this case, what information do you need to store to compute the function? I need to store the last bit, right? The bit that I just saw. That's all I need to store. So in some sense, you need to first figure out what I need to store and then how to update that information. And here, the information that I need to store is the bit that I just saw. Okay. And how to update that information is often, you can then get to it. So as suggested, let's do 2 states. And this is supposed to say that bit just seen is 0. Bit just seen is 1. Okay, that's our that's what we have in mind for these states. Okay, these are just labeled 0 and 1, but the state 0 signifies to us that the bit I just saw is 0. Okay, so I'm here, and if I see a 0, what should I do? If I'm at 0 and if I see a 0, what should I jump to? Yeah, jump to 0 back. Okay, and if I see a 1, just jump to the state saying you just saw a 1. Okay, and the same thing for the transitions out of the bit state 1. Okay, so if I see a 1, what do I need to do? I just stay there. And if I see a 0, I jump. Okay, make sense? All right, so this specifies working? Hold on. How do I pause the recording?
Recording in progress.
All right. Hold on. There's still some echo. I think this should fix it. We are back in full resolution. The audio and video should be much better now. And where were we? Okay, I remember my last state, which was trying to compute the last bit of the string. So let's continue from there. So we designed this automaton now. We have all the transitions that we need to figure out what function to compute, or do we? We're missing still one piece of the puzzle, right? Which is the set of accepting states. The description of the automata is not complete until I also tell you what will make you output 1 and what state will make you output 0. So in this case, what should the accepting state or states be? 1, right? And as we discussed last time, we'll indicate it with a double circle. Okay? Any questions about this? All right. Now, maybe let me do a small change to this function. What if instead of computing the function as above, I flip it? Okay. Now I want my function to say 1 if x ends in 0 and 0 otherwise. Okay. How can I design a finite automata for this? What's a simple way to get an automata for that? Any guesses?
We just flip the accepting state.
Yeah, right. So if you just flip the accepting state, then I'll compute the new function. The reason is, again, think like the automata, right? So to decide on what f is asking me to do, I just need to keep track of a little bit of information. And what's that little bit? What's the bit that I just saw? Okay. And based on that, I can compute it. Okay. So the only change I need to make is redraw it. Yeah.
But our starting state is 0, right?
Right.
So wouldn't that we got an empty, right?
Right. Okay. So that's a good point. You know, we, as given, that means that we also accept the empty string. That's an excellent point. And, you know, maybe that's what our function is. Or if you don't want that to happen, what I can do is, what should I do then? Any suggestions? Yeah, I could do that too. So, okay. So to make sure that I don't accept the empty string, I just switched the names given to the states, right? The transitions are kind of still the same. So whenever the last bit I see as 0, I end up in the state now named 1, okay? And that's when I accept. Any questions about this? So the name of the states is not of real significance in what the function is computing, right? It's just like what names you give to variables in your program is irrelevant to the final output of the program. right? As long as you're consistent within the program, what name you choose is not important, okay? But just as a convention, we always said, okay, we're going to start with the start state being 0. Any questions about this? Okay. So let's do a couple more examples. Often, sometimes it requires some ingenuity in coming up with finite automaton. But I'd say if you face a problem like that, what you should do is try to picture what information you need to output to compute the function. What's the minimal amount of information you need, and then kind of start with that, right? And if you start drawing diagrams, you'll see it. You might not see the entire picture right away at the beginning, but since it's kind of a visual thing you can play with, if you start experimenting, you might end up with the right automaton. Okay, so let's do one more. Let's do a couple more examples. And this one is maybe a bit more involved. All right, so I want a DFA that accepts only strings that have an alternating pattern. Okay, meaning, so my function that I'm trying to compute, so again, this is two different ways to talk about the same thing. I can say, okay, this is the function that I want your DFA to compute, or equivalently, I can also say these are the strings that your DFA should accept. Okay, when I say, okay, DFA accepts the string, that's just saying that the output of the function on that string is exactly 1. Okay, you can think of the DFA as some kind of filter, right? It says, okay, you are rejected, this string is rejected, this string is accepted, based on whether the function that you're trying to compute is 1 or 0. Okay, so the function that we're trying to compute is 1 if x has alternating zeros and ones and 0 otherwise. Okay, so for instance, f of 0, 1, f of 1, 0, 1, f of 1, 0, f of 1, 0, 1, 0, 1, these all should be 1. Okay, at the same time, if I say 0, 0, or f of 1, 0, 1, 1, or f 1, 0, 1, 0, 0, 1, 0, these all should be 0. Okay, any questions about the specification of the function? Right, if it's alternating, we need 1, otherwise 0. Yeah. Yeah, so let's say again, it's part of the specification. So let me say that then you output 1. Okay, we can do it either way. Let me just say that you're outputting 1. Yeah.
By alternating, so you're saying directly alternating between zeros and ones, right?
Yes.
0, 0, 1, 1, 0.
0, 1. Wait.
So like 0, 0, 1, 1, 0, 0.
No, that should be rejected. Basically, you should always click between 1, 0, 1, 0, 1, 0. Okay. So for instance, f of 0, 0, 1, 1, 0, 0, 1, 1, this should be 0. Okay. Basically, another way to think about it is if in your entire string at any point there are 2 bits which are exactly the same, then you have to flag that string as reject. Okay. All right. So how can I design an automata for this string? Any guesses? Well, let's, instead of just trying, let's become an automata, right? So I need to decide if I'm only seeing one, like I'm flip-flopping between 0 and 1 at every bit. Okay, so initially I don't know what I'm doing, so I'm going to start drawing this diagram. Okay, that's my start state. Okay, one step done. How about the rest? So now I have to start drawing transitions. Okay, intuitively, what information do I need to keep track of to decide the function? Yeah?
What's the most recent bit that you received?
Okay. All right, so let's start with that. So, I want to keep track of what's the bit that I saw, right? So maybe this is the branch which tells me, okay, you saw a 0. And this is the branch that tells me you saw a 1, right? And remember, the label associated with the state is of no particular importance, okay? But it's not just enough to keep track of one bit, right? I have to check alternating. So what do I really need to keep track of? Yeah?
If the rest of the string was alternating.
The rest of the string was alternating. But that's somewhat like, if I just know whether the rest of the string was alternating and I see a 0 or 1, that's not enough, right? For instance, what if I saw 101, which was alternating, but then I see a 1? Versus I see 010 and then I see a 1. Yeah?
Whether you already failed.
Whether what?
There should be a failure state.
Right, they should be a failure state. And basically, what you're really trying to do is keep track of the last 2 bits, right? Like what was the previous bit and what's the bit I just saw. If these two are somehow the same, I can declare failure right away. I know that the string is going to be rejected. No matter what you do for the rest of the length, you are a failure, okay? That's a slip, but all right. Okay, so if I'm on this branch where the last bit I saw is a 0 and I see a 0, I need to reject that string. Okay, so let me call that a dead state. Okay, and there's an easy way to do dead states. Okay, somehow that's sort of saying, okay, you are not going to lead to an acceptance state. What's an easy way to do a dead state? So once I reach this state, I might still see many bits. Yeah, exactly. Right, so 0, 1. Okay. Again, the single arrow with 0, 1 is shorthand for 2 arrows, both denoting 0 and 1. Both lead to itself. Okay. So if I'm on the state where I saw a 0 and I see a 0 immediately, then I reach the dead state. If I have a state where I saw a 1 and I see a 1 immediately, I go to a dead state. That much is clear. But now I'm still not done, right? If I'm here and I see a 1, what should I do? Yeah, as it says, as suggested, as gesture, I should go here. Okay? In some sense, intuitively, these states, the meaning that they're conveying is what was the bit that you saw previously. Okay? So if I see a 1, I go to down, and if I see a 0, I go here. Okay? All right? Okay, so now all the transitions are specified, right? Remember that whenever you draw or describe a DFA, you need to specify all the transitions. You might think, okay, these are going to some dead state, but you have to draw them, you have to specify them, right? Because otherwise the function is not complete. Okay, so all the transitions are specified. meaning every state has two outgoing edges. Now, what should the accepting states be? So this is the transition diagram, but what should the set S of accepting states be? Any guesses? 1 and 2. Okay, let's start with that. Yeah? All right. Okay, that's it. So now we have an automaton which satisfies all of these properties, right? Whenever you see an alternating string, you stay within here. But if I see two bits, that two consecutive bits which are the same, then I jump to a dead state and dead. Okay? Any questions? Yeah? Yeah, so actually that's a good point. My specification was not entirely accurate because I didn't tell you what you should do on the empty string, right? The empty string, let's say, should also be a 1, okay? If you want the empty string also to be accepted, then I just make this, okay? If not, if I say, okay, empty string is not accept, then I don't put the 0, the double circle on the 0 state. Okay, yeah?
So for DFAs, is it not possible to like exit right away? When we go to the dead state, it's still gonna keep.
Right,
We
yeah.
leave it until the end of the exit. But technically, once you hit the dead state, we have enough information to just say this is not an alternate path.
Right. So, I mean, this is essentially doing the same thing, right? But syntactically, you're not supposed to do that, right? Every bit you see, you're just kind of staying where you are. It's a way to do the same, to get the same functionality as you're asking, right? But kind of being consistent with the basic definition. So we don't have to introduce extra cases. But that's a good question. Like, somehow here we have this sort of sudden reject property, right? If I see two bits at any point which are the same, I know that the string is going to be rejected. Okay. But you can also consider the flip scenario where somehow you can make a sudden accept, right? Like, you solve this problem, then you get an A+ no matter what you do in the rest of the course. Okay. Something like that. And you can build a state like that too. Just call it a sudden accept state. You can kind of achieve the same functionality as here. Okay. Any other questions? All right. So before doing, let's do one last example, and then we'll talk about the general principles that go into designing DFAs. Okay. You'll do several examples in the homework, and they'll also show up in the exam. But as I said, it's a lot of fun to figure out what the transitions should be to compute some function, and also to figure out when certain things are computable by DFAs. Okay. Okay. So let's do one more example. Right. And this one is going to be a little trickier, I think. Seemingly, I think intuitively seems less complex, but in the world of DFAs, it's a little bit, to me at least, is trickier. Okay. So I want you to design a DFA that only accepts strings whose starting and ending bits are the same. Okay. You might have a million length bit string, but I want to accept it only if the first and the last bit are the same. So for instance, here are some strings that would be accepted, right? 0, let's say, maybe 0, 1, 0, 1, 1, 1, 0, 0, 1, 0. Okay. Rejected would be anything where the start and the end are different. Okay. So that's the specification of the function that we are trying to compute. And the question is, how can I design a DFA to do this? Yeah?
You could have state 0 be the initial state.
Okay.
And then just like, and then have two transitions, one to the state 1, one to state 2.
Okay.
Either one can be 0.
All right, let's see.
And then both of those can also have edges to state 3 and 4, and then edges to state 4 and 5. Being 0 very.
Okay, so is there like
branches off.
Okay. No, but then you have to you can't keep branching off, right? You have to stop. All right, so I think all right, so you want these to branch off. Okay, let's say. And then
so the last step is to like add edges between 3 and 4 and 4, 5, and 6. But just to explain, state 1 is going to be where you end up if you start with a 0, and then state 2 is when you end up with if you start with a 1. So the goal is to have the ending bit the same as the starting bit. So state 6 is going to be an accepting state.
Okay.
And state
3
will be an acceptance state, and then you just have edges going from like state 3. If you get a 0, you end up at 3 again.
Right. Okay, I get it. Right. So let me abstract this suggestion. Right. So at first, when you look at this problem, it seems like it should not. It seems something that you need a lot of memory, right? Because you need to store something that you saw way in the past. But that's not really true. You only have to store it once. You're not changing it again, right? In some sense, your universe splits into two things, where first I see a 0, or maybe first I saw a 1. Okay? And once I know this branch, I can sort of modularize my thinking, right? I know the first bit was 0, and when I'm reading the rest of the string, the only thing I need to figure out is whether it ends in a 0. Okay, but we saw how to compute that using a finite automaton, right? In some sense, I'm saying, okay, you read the first bit. If it's a 0, for the remainder of the string, you have to check if it ends in a 0. Okay. Similarly, if I see a 1, for the remainder of this string, I have to check if it ends in a 1. Okay. But for both of those things, we saw programs before, right? We drew a DFA which checks whether input string ends in a 0. So maybe I can just copy this diagram over there. Okay, so I think that's what your suggestion was also. But let me sort of try to keep things consistent with what we were doing and just copy that diagram. Okay. So all right, I see a 1, I end up here. I call this state 1, this state 2. Okay, so I see a 1, and I guess well, I think I glued it in the wrong direction, so let me just redraw it. So I see a 1, and I see a 1, I stay here, 0, I go there, 0, I stay here, 1, I stay here. Okay, so this is the same diagram as that we had before, which checks whether the last bit I'm seeing is going to be 1. Okay, so and similarly, I need to sort of create a replica of this here, where I'm trying to check whether the last bit I'm going to see after the first bit being 0 is a 0. Okay, so if I see a 0, I stay right there. If I see a 1, I flip. 1, I stay right there. 0, I come back. Okay, so like the universe split into 2 here, branched off. Branch of strings starting with 0. Okay, and this is branch of strings starting with 1. Okay, and what should the accepting states be? 1 and 3. Exactly. Okay, so this is another thing, you know, that we can do just as we do in programming, right? We can build sort of glue pieces together if we can. Okay, yeah.
With this setup, wouldn't a single bit be an accepted state as well?
Yeah, but that is fine, right? The yeah, that's fine, right? Because just as we specified, it was part of the specification. If not, we just put like, you know, one more state in the front and you can modify it. Okay, it's a good question. Any other questions? Okay, so I mean, these are some examples of how to design DFAs, and let's now investigate what are the real properties. Okay, so what is their power? What sort of operations can we do on them? How can we put these things together? Can we put them together, and so on? Okay. All right. So let's take a 5-minute break, and when we come back, we start digging deeper into what DFS are and what they can and cannot do. Okay. So let's do a quick recap of what DFS are, right? So the anatomy of a DFA, right? So what are the main pieces that go into it? So you have the number of states, which we've been denoting as C, and it's a finite thing, right? So these are all quantities that are fixed and bounded. Okay, in the sense that you specified this, these are some fixed constants that do not depend on the input length. Okay, and what else? Transition table, just T, and set of accepting states, S. Okay, and this is subset of C, right? So if you're asked to design a DFA, you can, you know, maybe you can specify the transition table, just draw this entire table, but most often it's much nicer to draw the diagram. Okay, unless it's very, very complicated, you can draw the diagram. Or if you're putting pieces together, you can explain it in text as well. And what is unbounded, right? one is, they can process inputs of arbitrary length. So DFA, even if it has only 2 states, it can still compute on any number of bits, right? It can process strings of an arbitrary bit length. The sequence of states that DFA visits is also unbounded, right? In every bit you read, you have a state. It might be new, the same, but it is a different, sort of state of computation. Okay. Any questions about this? Okay. And sometimes if you're designing a DFA, and I know some of you are familiar with programming, so you can also think of, to come up with a DFA, you can think of coming up with a programming algorithm, just like a code, which does single pass over the input and only stores a constant bit of information. Any such algorithm you can convert to a finite automata. Right? But for us, you have to write down everything mathematically, but to come up with the right sort of diagram, you can keep that picture in your mind, right? So what's the information that I need to store? What's the smallest amount? What's the constant number of bits I need to store? And how do I update this information? Okay? And you might also encounter different terminology which talks about the same stuff, like DFA, DFAs and stuff. So let me just sort of say a few words about this other terminology, because in some other courses you might come across this notation. So DFAs are also known as finite state machines. Okay, they are both equivalent, 2 names for the same thing. And often, sometimes DFAs are described as so we had only 2 things that were going into the DFA: the transition table and the set of accepting states. Okay? But sometimes you will see it described in the following way, as a 5 tuple of things. And Q is meant to be this set of states. Okay? Technically, it can be any finite set. Right? I can call these states anything I want. It won't change the computation. But we are sticking, just for ease, to calling the state 0 to 1 through C minus 1. Okay, this is just standardization. Doesn't change the computation. I can call the states A, B, C, D, and it doesn't change what you're computing. Okay, we're just going to use numbers 0 through to C minus 1 for consistency. And sigma is called the alphabet. So far, our finite automata are only processing bit strings. Okay, but you can also imagine a model where you're processing, let's say, maybe alphabets, letters A through Z, right? You can try and think of the same sort of model of computation. I see a single element of the alphabet, and then I need to make a decision based on that. Okay, update my state, and then so on and so forth. Single pass constant memory would make sense, even if the input is not necessarily zeros and ones. It could be, maybe over the letters of the alphabet. Right? But this again doesn't really change the underlying model of computation. And for us, we're always going to stick to alphabet being 0 or 1. Okay? As we discussed right at the beginning, we are just going to push these details under the rug and assume that everything is just bit strings. And T is the transition function. Okay. Just as for us, S0 is the start state. Okay. When you talk about allowing arbitrary names, you also have to specify the start state. But again, it's just what's in a name, right? So we stick to the start state just being the one labeled 0. Okay. I could have called, like, maybe this state label 2 is the start state. That would define same model of computation. Okay, and S is the set of accepting states as before. If you look at some other textbooks on automata theory, like for instance Sipser's textbook, then you might see this notation. Both are really equivalent to each other. There's no difference between what they can and cannot do. Okay, we just simplified everything to only focus on two things: the transition diagram and the set of accepting states. Okay, yeah.
What sigma and TR?
Yeah, sigma is like, you can define a more general, seemingly more general notion of finite state machines, where you might not just see bit strings, but you might see letters, right? So the input could be, A, B, C, D, E, F, G, H kind of strings. Okay, but we're not going to, it's not going to change too much about what we're going to do. And as I said at the beginning of the course, everything for us, all the inputs are just binary strings. Okay, that's a convention that we're using, in some sense without loss of generality, because everything can be encoded back to binary strings. Okay, and T is the transition diagram. Just as we have the table, if you have a more general set of labels for the states, more general alphabet, then you need to define the T accordingly. Okay, so for every state and for every symbol that I see, I need to tell you what is your next state. Okay. Any other questions? Okay, and one more remark. You can assume that the input string is binary. That makes, that's something that they are willing to do. But there was a very good question at the beginning of the talk, which was, what if I'm not trying to compute a single bit? But what if my desired output is multiple bits, right? When I say accepting states, you're just saying, okay, the output is either 1 or a 0. That's it, right? What if I somehow want to compute the output is maybe many bits long? Okay, so a concrete way to ask that question is, why Boolean functions? Okay, so why only study functions which output a single bit? Okay, these are called Boolean because the output is just one of two possible values. What about more general functions? Okay, so I mean, in reality, in many cases, we're not just interested in computing a single bit, right? When I ask you to add two numbers, the output is multiple bits. You think of image classification, I have an image which I can encode as a binary string, but the output could be one of, maybe cat, dog, alpaca, whatever, right? Okay, it's not just one of two possible values. My desired computation is to compute a multi-bit output thing. So how do I bridge this gap? Is our model somehow deficient in this way? What do you think? If I have to compute multi-output functions, I want to say that it suffices really to only compute Boolean functions. In general, maybe not for the specific finite automaton world, but in general. Any ideas for why that might be true? Yeah?
Could we take the same approach we did for NAND circuits and just compute each bit separately?
Exactly, right? So the general reason why we study only Boolean functions is that in some sense it's a very clean model, and for most cases, it's actually sufficient to only compute Boolean functions. Okay? So that's very much of theoretical computer science, and in many other cases, you really, even if you have multi-output thing, you only study sort of binary outputs. Even in machine learning, when I say image, I want to classify an image as cat, dog, or something, in the training phase, you do something called one-hot encoding, where you basically first do cat versus the rest, dog versus the rest, right? So you somehow convert all these multi-output things into just one of two possibilities, okay? The two reasons: one is it's much simpler to study, and also, as I said, it's kind of universal. So let's elaborate on that idea, right? So the idea is that we can compute each bit separately. Okay. So more concretely, computing any function, even if the input is unbounded, the output is unbounded, can be reduced to computing a sequence of Boolean functions. Okay. Suppose I ask you to compute this arbitrary function f, where the number of output bits can also grow with the input bits, right? You know, if I think of addition, add of x comma y, the length of the output depends on how long your input is. Okay. So in principle, the idea of computing each bit works, but you have to be a little bit more careful than when we were doing circuits, because we didn't have a pre-specified bound on the output length. Okay. But I want to say that you can reduce this to computing a sequence of Boolean functions, right? Somehow I can iteratively compute a Boolean function to mimic the same behavior. Okay. How can I do that? Well, as suggested, I can try and compute each bit separately. So let me define define bool f. Okay, it's kind of a Boolean version of the input function f, which takes a string x as input, an integer I as the input, and it's supposed to indicate whether the ith bit of the output is actually 1 or 0. Okay, is f of x the ith bit of that if I is less than the length of f of x and 0 else. Okay, this is essentially computing each bit at a time. All right. Okay. So if I give you the power to do this bool f, then I can pretty much compute f. The only caveat is, you know, I might not know when the output is actually ending. Okay. So for that, I might, you know, another way to do it is to just say length f. Okay, so I'm defining these two Boolean functions. If you so desire, you can also compact them into one function, but you know that just obscures the picture. It doesn't change what we're doing. This is just a way to compute one bit at a time. Okay, yeah. So the length f is basically, it's kind of a way for me to check what's the length of the output, because I don't know a bound a priori. So it's going to say 1, 1, 1, 1, 1 until we hit the length of the output of f, and then it's going to transition to 0. Okay, any other questions? So if I have these two things, I can simulate the original function capital F using these two pieces, right? So imagine you're writing some program where, I gave you a library which has these two things implemented, okay? And I want to compute F. So what can I do? So let's say computing F using Boolean functions. Okay, so I'm just going to write some Python code. The syntax is not important. It just says, okay, you're going to start with the result being 0, empty, I equals 0, and while I'm going to check if my index is less than the length of the output. Okay, if so, then I'm going to add the new bit okay, and then increase the index. Okay, so I'm just computing one bit at a time as we originally thought of doing. The only sort of caveat or maybe trick here is to branch based on the length. Okay, I might not know when the length was, when the output, what the output length was, but that's being encoded as this Boolean function. Okay, so if I have the power to compute Boolean function, then I can compute any function of even arbitrary length. Okay, so that gives us this confidence to only focus on Boolean functions, where the output is only 1 bit long. Any questions about this? Yeah? Oh, that's concatenation, sorry. Concatenation. Okay, sure, yeah?
If F is computable, are length F and bool F necessarily computable as well?
In most cases, yes. Okay, but there are some cases where you might change the complexity of the problem. Okay, but in some sense, what does it mean to say F is computable without computing the individual bits? Right? So you can think of both. You can somehow, when you look at the fine-grained questions of how many resources you're exactly using, there may be a difference. But if I'm asking the most significant bit, is it possible to compute this function, then there's not usually any difference. Okay. Any other questions? Okay. So these are all sort of now we have like the entire fundamentals of DFA. We know what's the anatomy of a DFA. We're trying to compute Boolean functions. We've seen several examples. We know how to behave like one, kind of picture them in our mind and come up with DFAs in your sleep. But let's say what they are good for, right? When you think of programs, one of the most important things that we do is to reuse computations, right? Can DFAs allow us to do that? Okay. For instance, in that example where we had to compare the first bit and the last bit, we implicitly did that. We did a branch based on the first bit and then kind of reuse the DFA from earlier. Okay. So this notion of reusing stuff, somehow breaking up pieces and putting them together, are studied. The formal way of talking about them is closure properties. Okay, and this is something that you'll see a lot Actually, I mean, I'm sure many of you in any programming class would have used it, but the mathematical way of talking about them is closure properties. Okay. What does that mean? It says, for instance, suppose, I am in this world where someone gave me a DFA f, a function, okay, is computed by a DFA D1. Okay, I tell you, okay, here's a DFA which computes some function. And I also tell you, here's a DFA which computes another function. Okay, now you can ask, maybe certain things are defined by combining F and G. Okay, so imagine you're trying to build a filter, right? So you first check if the first and last bit are the same. Maybe you also want to check whether there are two consecutive bits which are the same, right? So can I compute the function h, which is AND of FMG? So I can define a new function which I'm going to denote as f and g, where h of x is exactly f of x and g of x. In some sense, this is like a filter, right? So the first DFA says, okay, these strings are accepted. It's like the first test. And the second DFA says, okay, these certain things are accepted. That's the second test. And now I have to figure out which strings pass both these tests. I give you pieces of hardware for these things. Can you, is the new function computable by a DFA or not? Can I ask, okay, maybe what if I have the OR? Okay. So closure properties really talks about these sort of basic operations that you can perform on functions. Okay. And this is again something important in practice. You might have controllers, some filters that you built using a finite state machine or a deterministic finite automaton, and now you want to combine them. Can you do it? In the world of circuits, it's kind of easy, right? And was a circuit, so I just put them, kind of copy them together and do it. But why might that not be easy in the case of DFAs? So when I ask you to imagine you're writing a program, right? I gave you an oracle which can compute F and an oracle to compute G. What would you do if I ask you to compute F and G? Well, I'll say, okay, compute F of X, compute G of X. Result is the AND of these two. Okay. Okay, let's see. Example. Def and FG. Okay, so I'll say it is A equals f of x, b equals g of x, return A and B. I just slow down the steps separately. If you were to write this in let's say my favorite programming language, this is exactly what I would do. Okay, I'd compute f of x, compute g of x, and return the AND of the two. But is this code a DFA. Can I convert it to a DFA? No, right? Why? Why not? Yeah, it's not single pass algorithm. I'm reading the input once to compute F, but then somehow, I'm going back and reading it again to compute G, but that is not allowed. Okay, so when you're doing in the definition of DFAs, this is not a single pass algorithm, even if F and G were single pass, right? F was reading 1 bit at a time, but then to restart the computation, I need to read 1 bit at the time from the beginning, which is not a single pass algorithm. Okay. So is there a problem somehow? Does this mean DFAs we cannot do AND of things if we can do the individual functions? Let's think of an example, right? Suppose I tell you there's a DFA that accepts X if number of ones is divisible by 2. Okay. And there is a DFA that accepts X if number of ones is divisible by 3. Now, what would be the AND of these two things? That accepts X if the number of ones is divisible by 6. Can I somehow combine these two DFAs to get a DFA that checks for the AND? Right? So this is like an example question to keep in mind. Right? So let's maybe be more specific about what we are trying to do. I have a DFA D1 on maybe some C1 states, which is given by a transition function T1 and a set of states S1. And I have a DFA D2 on C2 states, which has transition diagram T2 and states S2. Okay. And what's my goal? I'm asking you is D. Okay, let me not use D, that might be confusing. H defined as H of X is D1 of X and D2 of X computable by a DFA. So what do you think is the answer and how can I go about computing it? Our first attempt failed because it ended up not being a single pass algorithm. Okay. But luckily, or otherwise the model would not be very interesting, but you can actually compute ANDs of DFAs again as a DFA. Okay, there is a way to compute the AND still only doing a single pass. Any idea how I might be able to do it? Yeah?
Could you create a distinct state for each combination of two states, B1 and B2?
Exactly, right? So somehow again, think of yourself as a DFA, right? So imagine there's one person who is sort of simulating the behavior of the first DFA, that's one box, okay? And there's another person who is really, whose mind is second DFA. Okay. And if I want to make some decision which depends or remix and depends on both of their behavior, I can sort of put a big box around both of them. Okay. So my memory is going to be what both of them hold in their minds. And somehow imagine I'm moving pieces based on kind of simulating both of them at the same time. Does it make intuitive sense? Like somehow I'm combining both of them into a single piece. Okay. So formally, the way we'll do it is the following. So I'm going to define a new DFA where the number of states is C1 times C2. Okay, which means basically there's like, imagine there is the first set of blue states which correspond to the first DFA, the second set of red states which correspond to the second, first and second DFAs, and then for every possible position of the first and every possible position of the second, I need to tell you what you would do. Okay, how would each person behave? So the number of combinations is all positions the first person might be in, all positions the second person might be in. So intuitively, I'm going to identify the states as a pair I comma j, where I belongs to 0, 1 to C minus 1, C1 minus 1, okay. So I'm going to keep track of the memories of both of the finite automaton and update them simultaneously. Okay. So the transition diagram is going to be from the states to 0, 1, 2 states, right? And suppose I tell you that the first machine is in state A, the second machine is in state J, the memory contents of the first machine are I, the memory contents of the second machine are J, and you see a bit A. How should the memory contents be updated? Any guesses? You need to update both of them, right? Both of them take a step corresponding to their internal logic. Okay? So how can I do that? So what should the new state be when I have these two machines that I'm simulating at the same time? Any suggestions? Yeah? Exactly, right? So T1 of I comma A, which is I'm mimicking the first machine's behavior on the contents of the first memory, and T2 of J comma A. Right? So there are two people now hopping around, and we as a universal controller are instructing them how to move in some sense. Okay? All right, well, we're kind of done, but not quite. I still have to specify the accepting states. So what should the accepting states be if my goal is to compute the AND of the two DFAs? Yeah?
The set intersection.
Well, the two things are completely different worlds, right? They're like, the first memory is doing something, the second one is doing something else. By intersection, you mean like both of them should land in accepting states, right? Okay, so you're going to declare a success if the first player succeeded and the second player succeeded, right? And the first player succeeds if their memory contents lie in S1, which was the things that they were accepting, okay? And the second player would succeed if their memory contents are in S2. Okay. So if I talk about this as being my new DFA D, then D of X is actually equal to D1 of X and D2 of X. Okay. So on every input bit, on every input string, the behavior is exactly as the AND of the two things. All right. So compared to the trivial algorithm we saw earlier, the memory cost here was much smaller. Somehow we reused the memory when we said, okay, compute f of x and then compute g of x. So we could reuse the memory there, right? But you had to do double pass to do that. And what we're doing here is using extra memory, but going through the input only once, which is what we need to do the computation as a DFA. Any questions about this? So the summary is AND of DFAs is computable by DFA. Okay. In some sense, if I told you, okay, these two things are computable by DFAs, then their AND is also, right? And one terminology for this is that DFAs are closed under ANDs. Okay, it's really the same thing. Saying closed under ANDs means that basically, imagine you're looking at all functions that are computable by DFAs. If I take two of them and AND them, I'm still in the same class. Okay, so even if I AND, I'm always staying within the same class of things that are computable by DFAs. Okay. All right. So there's an alternate way of looking at the same thing, and that's in terms of the languages. So we had DFA D1. So maybe this corresponds to language L1. Okay. And then DFA D2 corresponds to language L2. Okay. What's the language that corresponds to the AND of the two DFAs, to the two functions? In terms of sets, when I take the AND, what does that do to the set of accepting strings? The first one should accept, the second one should accept. So language of D1 and D2 is somehow AND, taking AND in the function world corresponds to taking intersection in the language world. Okay, this is again just nomenclature, really doesn't change what you're doing. If I ask you to compute the AND of the two functions, that means that I'm essentially taking the intersection of the languages that you're accepting, right? Why is that? Well, think of the elements here. A string X is an L1 intersection L2 if you lie in both, meaning the first one accepted and the second one accepted. It's like filtering, right? Before you had to pass the first filter and you had to pass the second filter. That's equivalent to intersection. All right. So sometimes you might also see this stated as DFAs are closed under intersection. Okay, this is all the same phenomenon, different ways of saying the same thing. Okay, so before going on, I want to ask, let's end with Question. What about or? Meaning D1 or D2. If D1 and D2 have two DFAs, what if I want to compute the OR of the two things as a DFA? Can I do that or can't I? If I want to do it, what should I change in this construction? Any suggestions? Yeah? Exactly, right? So pretty much the entire thing stays the same, and the only thing we need to change is the definition of accepting states, right? So basically, as long as we have the entire behavior of the two machines simulated in parallel, we can change what you do at the very end as required, right? So So the only thing I need to change, as exactly guessed, is to make this set of change the set of accepting states. Okay. So the DFAs are closed under taking the OR operation too. And computing OR of D1, D2 is equivalent to dash on the languages. Fill in blank. So let's say, so what does the language of D1 or D2 correspond to? Suppose I had the language of D1 was L1, language of D2 was L2. What corresponds to the language of the OR of the two functions? Yeah? Union. Okay. So this is union. Right? So now we have kind of a nice sort of verbal way of saying things. DFAs are closed under union. They're closed under intersections. If I take the state of all things, languages computable by DFAs, then taking the intersection also gives me a language that is computable by DFAs. Okay? And we'll study a few more closure properties next Monday, and then we'll take it from there. Just as a warning though, it kind of seems obvious that these closure properties should be satisfied for any reasonable model of computation. Okay? But sometimes even interesting models of computation do not satisfy these closure properties, or when they do, it's highly non-trivial to understand it. Okay? And we'll talk about these things in the next class as well. Okay. I'll see you on Monday, and remember, assignment 2 will be out today.